Okay, so last week we talked about last lecture, we talked about what statistics are and why they matter. We talked about populations and samples, about the catastrophic failures of psychology, lobotomies, recovered memories, and how those failures happened because people weren't measuring properly and they were trusting their intuitions instead of checking their beliefs against reality. So today we're going to dig into something more fundamental, something that underlies everything else we'll do in this course. We're going to talk about measurement, okay? And I want to start by pointing out something that may not be obvious. Measurement seems simple. It seems straightforward. You want to know how tall someone is, you get a ruler. You want to know how much they weigh, you put them on a scale. You want to know how fast they can run, you use a stopwatch. So measurement appears to be a solved problem, right? Just find the right tool and read the number. But the thing is, psychology doesn't measure height or weight or speed. It measures, intelligence, depression, anxiety, personality, self-esteem, motivation, happiness, and those things are different, okay? You can't point to intelligence. You can't hold up depression and examine it. You can't put anxiety on a scale. These are what we call abstract constructs. They're theoretical entities that we believe exist, that we believe influence behavior, but we can't directly observe. And that creates a problem. It's a fundamental problem that underlies almost everything psychology does, and that psychology has never been able to fully solve and probably can't. The problem is this: how do you measure something you can't see? How do you know your measure is actually capturing the thing that you care about? And how do you know you're not just measuring something else entirely? Something that looks like the thing, that correlates with the thing, but isn't actually the thing, okay? So this is the problem of what we call operationalization. And it's not a technical footnote, it's the central challenge of psychological science. Get that wrong and everything downstream is contaminated. Your statistics might be impeccable and your sample's perfect, your analysis is brilliant, but if you're measuring the wrong thing, none of that matters. Garbage in, garbage out. So no amount of sophisticated statistics can fix bad measurement, okay? What is a variable? Before we can talk about measurement, we need to talk about what we're measuring. And the basic unit of measurement in statistics is the variable. So a variable is anything that can take on different values. And that's the definition. Anything that varies. Anything that's not the same for everyone or everything you're studying. Height is a variable. Different people have different heights. Political affiliation is a variable. Some people are Democrats, some are Republicans, independents, some are something else. Reaction time is a variable. Some people respond faster than others. Mood is a variable. It changes across people and within people over time. Intelligence is a variable. Whatever it is, it differs across individuals. And the opposite of a variable is what we would call a constant, something that doesn't change within your study. If you're only studying 20-year-olds, age is a constant. Everyone is 20. If you're only studying women, gender is a constant. Now, whether something is a variable or a constant depends on your study design. Age varies in the population. People are different ages. But if you decide to only include 20-year-olds in your sample, you've made age a constant for your purpose. You've held it constant, and that's a choice. Every time you include or exclude something, every time you hold something constant, you're making a choice. And that choice has consequences for your research. Why would you hold a variable constant? Usually for control. If you want to know whether a drug affects memory and you're worried that age might also affect memory, you might decide to only study people of one age. That way, any differences you find can't be due to age. Age is the same for everyone. That's good for internal validity or for being confident that the drug, not age, caused any differences you observe. But it's bad for generalization. So if you only study 20-year-olds, you can only confidently generalize to 20-year-olds. Maybe the drug works differently in older people. Maybe it doesn't work at all. Okay? You don't know because you held age constant. So there's a trade-off. Holding things constant gives you control, but limits your ability to generalize. Including variation gives you breadth, but makes it harder to isolate specific effects. The point is, choices about variables are not just technical, they're theoretical, and they can determine what you can learn from your research, and you should make them consciously with awareness of those trade-offs, okay? One more thing about variables. Variables have possible values. The range of values is important. So think about stress, a stress measure, like with a 0 to 4 scale. There's 5 possible values, 0, 1, 2, 3, 4. That's it. The scale constrains what values are possible. Now think about age, right? There's lots of values, 0, 1, 2, 3, all the way up to however old people get. And that range is much wider. Or think about gender, okay? If you're measuring gender as a simple category, male or female, there's only 2 possible values. But nowadays, we might open up our research to all sorts of values, Or think about religion. How many categories are you going to include? Christian, Jewish, Muslim, Hindu, Buddhist, atheist, anything else. The number of possible values depends on what you've defined as the variable. And this matters because the possible values shape what statistical analyses are appropriate. We'll come back to this when we talk about levels of measurement, but for now, just notice variables aren't just things that vary. They have a structure, a set of possible values, and that structure matters. Okay. Now we come to what I consider the most important and most difficult topic in this entire course. There's a distinction that you need to understand deeply, and it's the distinction between constructs and operationalizations. And if you don't understand this distinction, you'll make mistakes. You'll fool yourself. You'll draw conclusions that aren't warranted. So what is a construct? A construct is the abstract theoretical thing you actually care about. Intelligence is a construct. Depression is a construct. Extroversion, anxiety, self-esteem, motivation, happiness, creativity, they're all constructs. It depends on what you're studying, what you find important. These are theoretical entities. They're things we believe exist. We believe there's something called intelligence that differs across people and that explains why some people learn faster, some solve problems better, adapt to new situations better. We believe there's something called depression that some people have and others don't and cause certain patterns of symptoms. But we cannot directly observe constructs. We can't see intelligence. We can't point to depression. We can't put anxiety under a microscope. Constructs are inferred. They're theoretical. They're believed in, but not directly observed because they're not a thing that you can actually observe. Okay? An operationalization is the concrete procedure or measure you use to try to capture the construct, to try to measure it. If intelligence is a construct, IQ test is the operationalization. If depression is a construct, the Beck Depression Inventory is the operationalization. Anxiety is the construct. Have people rate their anxiety on a scale of 1 to 10. That's the operationalization. So operationalizations are observable. They produce data. You can actually do them and get numbers. But the crux of the problem is your operationalization may or may not actually capture your construct if you're not careful. When you give someone an IQ test, you get a number, but is that number actually measuring intelligence? Or is it measuring something else? Test-taking ability, familiarity with certain kinds of problems, cultural knowledge, their motivation on that particular day. So when you give someone a depression questionnaire, you get a score, but is that score actually measuring depression? Or is it measuring, willingness to admit to negative symptoms, or maybe a cultural script about how you express distress, or that the person has a tendency to complain, or something else entirely. So the gap between the construct and the operationalization is where all that uncertainty lives. And in psychology, that gap is often very large. Okay? So let's look at a case study. Okay, let me walk you through this carefully with intelligence because it's the most well-studied construct in psychology and it illustrates the problem perfectly. So first ask yourself, what is intelligence? Is it the ability to learn, the ability to solve problems, the ability to adapt to new situations, the capacity for abstract thinking, the ability to acquire knowledge, all of these, some of these? Is there one intelligence or are there multiple intelligences? Is intelligence fixed, something you're born with, or is it malleable and can be developed? Is intelligence the same across cultures, or does it mean different things in different cultures? So these are not settled questions. Psychologists have debated them for over a century, and there's no consensus on what intelligence actually is. And yet we have IQ tests. We have operationalizations. So what does an IQ test actually do? It presents you with puzzles and problems, pattern recognition, vocabulary, arithmetic, spatial reasoning, and it measures how well you do these puzzles. It produces a number. That number predicts certain things: school performance, job performance, income, even life expectancy. People with higher IQ scores do tend to do better on these outcomes. So the IQ test is measuring something real. It's not random noise. It predicts things. It's reliable. Give it twice and you get similar scores, but is it actually measuring intelligence? Supporters of IQ testing argue that yes, obviously, the test predicts exactly the things you'd expect intelligence to predict. It's the best validated construct in psychology. Alternatives are there, but they're kind of vague and fuzzy. This is as close to measuring intelligence as we've gotten so far. On the other hand, critics argue that no, not really. The test measures a kind of cognitive ability, the kind valued in Western academic settings and schools. It doesn't measure practical intelligence, like the ability to fix things, navigate social situations, survive in difficult environments. It doesn't measure emotional intelligence, how we understand and manage emotions in ourselves and others. It doesn't measure creative intelligence, our ability to generate novel ideas and solutions. Critics also argue the test may be culturally biased, so it assumes familiarity with certain concepts and certain ways of thinking that are more common in some cultures than others. And it might confuse knowledge with ability, penalizing people who haven't had access to certain information. So who's right? And the honest answer is we don't really know. We don't fully know. We don't know whether IQ tests measure intelligence because we don't fully know what intelligence is. We have a construct, this theoretical thing we call intelligence, and we have operationalizations, IQ tests, and we're not certain whether the operationalizations capture the construct. This is not a failure of psychology. This is the human condition when it comes to measuring abstract things. That gap between what we care about and what we can observe is, it's inherent to all of this, inherent to the enterprise, but you need to be aware of it, okay? You need to hold your conclusions lightly, like I said last time. You need to remember that when someone reports an IQ score, they're reporting the result of a particular operationalization, not a direct measurement of this thing we call intelligence. Okay. So here's something that makes this even more complicated. The same construct can be operationalized in different ways. Take intelligence. You could operationalize it as 1, a score on a verbal SAT test, 2, speed of task performance, how fast can you repair an engine, for an example, 3, the standard IQ test score, 4, self-rated intelligence, just ask people how smart they think they are. These are all plausible operationalizations of intelligence. They all capture something that might be related to what we mean by intelligence, but they're different. They measure different things. Someone who scores high on the verbal SAT might score low on engine repair speed. Someone who rates themselves as highly intelligent might have a mediocre IQ score. So which one is right? Which one actually measures intelligence? And the answer is, it depends on what you mean by intelligence. Different operationalizations embody different assumptions about the construct. When you choose an operationalization, you're not making a neutral technical decision. You're committing to a particular understanding of what the construct is. This means one variable does not equal one definition. You have to choose. Different researchers might operationalize the same construct differently. Both might be valid in some sense, but they might be measuring slightly different things. So as a reader of research, you should always ask, how did they operationalize this? And does that operationalization actually capture what I care about? Okay. Another example, depression. What is depression really? Is it a brain state, certain neurotransmitter levels, certain patterns of brain activity? Is it a pattern of thoughts, negative beliefs about yourself and the world and the future? Is it a response to circumstances? Loss, failure, hopelessness? Is it all of these? Something else? We don't know, okay? Depression is a construct. We believe it exists. We believe it explains certain patterns of suffering, but we don't have direct access to it to measure it. Now, one common operationalization of depression is the Beck Depression Inventory. It asks questions about sadness, guilt, pessimism, sleep, appetite, and so on. It produces a number, but what is that number actually measuring? Is it measuring depression, or is it measuring willingness to endorse negative statements about yourself? Is it measuring a cultural script? What people in this culture think depression is supposed to look like? Is it measuring how people want to present themselves? So the concrete problem is that different cultures respond differently to depression questionnaires. In some cultures, people express distress through physical symptoms like headaches and fatigue and pain rather than emotional language. And so they might score low on a depression questionnaire that asks about sadness and guilt, even if they're very profoundly depressed. So is the questionnaire invalid in those cultures? Or do those cultures have different kinds of depression? Or is the very concept of depression culturally specific and not universal? These are hard questions. They don't have easy answers, and they illustrate the fundamental problem. There's a gap between construct and operationalization, and it's not just a technical issue to be solved. It's a deep uncertainty that we have to live with. Okay. One more example, self-esteem. This is a case where the problem is even worse because we don't even have a clear theoretical understanding of what the construct is, like we do with intelligence and depression. So what is self-esteem? Is it a feeling about yourself, how you feel when you think about who you are? Is it an evaluation, your judgment of your own worth? Is it social comparison, how you see yourself relative to others? Is it a defense mechanism where you're protecting yourself from threats to your ego? Different theories give different answers, and different operationalizations follow from different theories. So if self-esteem is a feeling, you might measure it by asking people how good they feel about themselves. If you think it's an evaluation of their self-worth, you might ask them to rate their own qualities. If you think it's social comparison, you might measure how they see themselves relative to their peers. But these might actually be measuring different things. Someone might feel good about themselves, but rate their qualities as average. Someone might see themselves as better than their peers, but still feel bad. So which operationalization is right? Which one measures real self-esteem? And the answer is we don't know, because we don't know what self-esteem is. The construct itself is unclear. And when the construct is unclear, no operationalization can be definitively correct. Okay, here's what I want you to take away from all of this. When you decide how to measure something, you're committing to a particular theory, a particular understanding of what that thing is. You're making a theoretical claim, not just a technical decision. If you operationalize intelligence as IQ scores, you're implicitly claiming that intelligence is the kind of thing that IQ tests measure. If you operationalize depression as the Beck depression inventory, you're implicitly claiming that depression is the kind of thing that questionnaire captures. You should be aware of these implicit claims, these biases. You should be able to articulate them, and you should hold them with an appropriate level of uncertainty. Don't mistake your measure for the actual thing you're measuring. The map is not the territory, okay? The operationalization is not the construct. They're related, hopefully closely related, but they're not the same thing. And this matters because most psychological constructs have uncertain validity. We don't know for sure that our measures capture what we think they capture. And this uncertainty propagates through everything we do. If the measure is wrong, the statistics are meaningless. If the operationalization doesn't capture the construct, the conclusions don't matter. They don't follow. This is one source of psychology's replication crisis. Researchers measure something, they find an effect, they claim they've discovered something about the construct, but maybe they've only discovered something about the operationalization, something specific to that particular measure that doesn't generalize. Okay. Let's talk about level of measurements. Okay, this is something more technical, but it's equally important. When you measure something, you get numbers, okay? But not all numbers mean the same thing. The kind of numbers you have determines what you can do with it, what mathematical operations are meaningful, what statistics you can compute. So this might sound pedantic and picky and stuff, but it's not. Ignoring levels of measurement leads to meaningless results. You can compute numbers that look impressive, but actually mean nothing. The computer will give you an answer, but whether that answer makes sense is up to you doing this correctly. So the framework I'm going to present comes from a psychologist, S.S. Stevens, who developed this classification in the 1940s. And it distinguishes 4 levels of measurement: nominal, ordinal, interval, and ratio. Each level has more structure than the one before, and each allows more mathematical operations. So level 1, the most basic level of measurement, is nominal. Nominal measurement is just categorization. You're putting things into categories, but the categories have no inherent order. Think about gender. Male and females are categories, but neither is more than the other. They're different, but not ranked. Political affiliation, Democrat, Republican, Independent. These are categories. You can belong to one or another, but they're not ordered. Being a Republican isn't more or less than being a Democrat in any mathematical sense. Eye color, blue, brown, green, hazel. Those are categories without order. Psychiatric diagnosis, schizophrenia or major depression. These are categories. You have one or another or none, or maybe more than one, but they're not ranked, okay? So what can you do with nominal data? Not much mathematically. You can count how many people are in each category. You can compute proportions, what percentage is male, what percentage is female. You can compute the mode, the most common category, but you can't compute a mean. You can't say what's the average gender. That question doesn't make sense. What's the average political affiliation? That's meaningless, okay? Now here's a trap. Sometimes people assign numbers to nominal categories. Male equals 1, female equals 2, or Democrats 1, Republican 2, Independent 3. The computer will happily compute an average of these numbers. It might tell you the average political affiliation is 1.7, but that's meaningless, right? It doesn't represent anything real. So the numbers are just labels. They're arbitrary tags we've attached to categories. You could just as easily have made Democrat 47 and Republican 3. It doesn't matter. The average would be different, but equally meaningless. So just because you can compute something doesn't mean that you should. So the numbers have to mean something for the computation to be sensible. There's a special case of nominal variables worth mentioning, dichotomous or binary variables. So these are nominal variables with only 2 categories, yes or no, male or female, employed or unemployed, pass or fail. They're still nominal categories without order, but having only 2 categories sometimes allows special statistical treatments. Okay, we'll talk about that more later. All right, the next level up is ordinal. Ordinal measurement has categories, and the categories are ordered. Ordinal, ordered. There's a ranking. First is more than second, second is more than third. But, and this is crucial, the intervals between categories are not necessarily equal. Think about race finishing positions, like first place, second place, third place. There's an order. First is better than second, second is better than third, but the intervals aren't equal. First place might have finished 10 seconds ahead of second place, while second place finished a fraction of a second ahead of third. The ordinal ranking doesn't capture this. It just tells you the order, not the distances. Education levels, high school, bachelor's degree, master's degree, PhD. There's an order. PhD represents more education than master's, which is more than bachelor's, and so on. Okay, but the intervals aren't equal. The difference between high school and bachelor's might be 4 years. The difference between master's and PhD might be 5 or 6 years. The time, effort, difficulty, they're not the same across levels, okay? And the amount you learn isn't the same either. Think about dress sizes, 0, 2, 4, 6, 8. They're ordered. Size 6 is bigger than 4, but the actual physical difference between sizes isn't necessarily the same across the range. Okay, Likert scales, and this is where it gets really important for psychology. For instance, rate your agreement on a scale from 1 to 5. Strongly disagree, disagree, neutral, agree, strongly agree. There's an order. Strongly agree represents more agreement than agree, which represents more than neutral, and so on. Okay, but are the intervals equal? Is the psychological distance between strongly disagree and disagree the same as the distance between agree and strongly agree? Probably not. Okay, people who are dissatisfied might feel very strongly about it. Jump from very dissatisfied to dissatisfied might be large psychologically, but people who are satisfied might not distinguish much between satisfied and very satisfied. Okay, the jump might be small. And different people might interpret the labels differently as well. So what I call agree, you might call strongly agree. The scale means different things to different people, okay? The intervals are almost certainly not equal, which means Likert scales are ordinal, not interval. So here's a dirty secret about psychology. Most psychological research treats Likert scale data as if it were interval level data. Researchers collect ordinal data, 1 to 5 ratings, 1 to 7 ratings, and then they compute means and standard deviations. They run t-tests and ANOVAs. They do correlations, all these things we'll talk about later. All of these procedures assume interval level measurement. They assume that the intervals are equal, that the difference between 1 and 2 is the same as the difference between 4 and 5, but the data are ordinal. The intervals are not equal. Is this a problem? Sometimes yes, sometimes no, and usually we don't know which. If the intervals are approximately equal, if the violation of the assumption isn't too severe, the analyses are probably fine. The results are approximately right. But if the intervals are very unequal, if the scale is seriously nonlinear, the results might be very misleading. So a statistically significant difference might not represent a meaningful psychological difference. So the numbers might look impressive, but not mean a lot. The computer doesn't know, the computer just computes. It doesn't know whether your data are nominal, ordinal, interval, or ratio, although with AI that might change. It doesn't currently know whether your computation makes sense. It just does what you tell it to do. So you have to know. You have to understand what level of measurement you have and what analyses are appropriate. And what's the alternative? You could use ordinal statistics, medians instead of means, rank-based tests instead of t-tests. These don't assume equal intervals. They're more conservative, they're less powerful, but they don't violate assumptions, so they're less likely to be wrong. Or you could try to develop truly interval level measures where the intervals really are equal. And this is difficult and it's rarely done in practice, but you can do it. Or you could acknowledge the limitation and interpret your results cautiously in your discussion section. So recognize that your mean of 3.8 versus 3.2 might not actually represent a meaningful difference, even if it's statistically significant with ordinal data. What you shouldn't do is pretend the problem doesn't exist, because it does. The third level is interval. Interval measurement has equal intervals. The distance between any two values are the same. So the classic example is temperature in Celsius or Fahrenheit. Distance between 20 and 30 is the same as the distance between 30 and 40 degrees. Both are 10 degrees. The intervals are equal. And this means you can do arithmetic with these numbers, and you can compute the means, the standard deviation. But here's the thing about interval scales. They don't have a true zero. The 0 point is arbitrary, not an absence of the thing being measured. So 0 degrees Celsius is the freezing point of water, is not the absence of temperature. There's still temperature. There are temperatures below zero. Negative temperatures exist. 0 point is a convention. It's not a natural boundary. And this means ratios don't work. You can't say 40 degrees Celsius is twice as hot as 20, because it's not. To see this, convert Fahrenheit. 40 Celsius is 104 Fahrenheit. 20 Celsius 68 is 104 twice 68. No. Okay. So IQ scores are typically treated as interval. The distance between 100 and 115 is the same as 115 to 130, 15 points, but there's no true zero. An IQ of 0 doesn't mean no intelligence. And you can't say an IQ of 130 is twice as intelligent as 65. Calendar years are intervals. There's no true year zero in most calendars. With interval data, you can compute means and standard deviations. You can do t-tests, ANOVAs, correlations, regressions. Most of the statistical procedures you'll learn in this course assume at least interval level data. Okay. The highest level of measurement is ratio, highest meaning most complex. Ratio scales have everything interval scales have, plus a true 0 point. So 0 means the complete absence of the thing being measured. Height, 0 height means no height at all. 0 weight means no weight. 0 time of reaction means no time passed. 0 income literally means 0 income. So with the true 0, ratios are meaningful. Someone who is 6 feet tall is twice as tall as someone who is 3 feet. Someone who earns 100,000 earns twice as much as someone who earns 50,000. Someone who takes 200 milliseconds to respond took twice as long as someone who took 100 milliseconds. You can do any mathematical operation with ratio data. Add, subtract, multiply, divide. All statistics are appropriate. But there is a problem here for psychology. Few psychological constructs have true zeros. What would zero intelligence mean? A complete absence of any cognitive ability, like a vegetable? It's not really conceivable. What would zero personality mean? What would zero anxiety mean? Absolute calm, never experiencing even the slightest worry? These concepts don't have natural 0 points. So most psychological measures are interval at best, and many are really ordinal despite being treated as interval. Okay, so let me summarize the 4 levels. You have nominal, categories only, no order. You can count and compute proportions. Examples, gender, political affiliation. Ordinal, categories with order, but intervals are not necessarily equal. You can rank and you can compare, like your education level. Interval, equal intervals, but no true 0. So you can compute means and do most statistical tests. And then ratio, equal intervals plus a true 0. So all mathematical operations work, height, weight, reaction time, income level. The level of measurement determines what you can do with your numbers. So just because you can compute something doesn't mean you should. The computation has to make sense given the kind of data you have. So you have to know what your data is. All right, now let's talk about what makes measures good. Okay. There are 2 main criteria, reliability and validity. They're related but different, and you need to understand both. Reliability is about consistency. Does the measure give the same result under the same conditions? Think about a bathroom scale. If you step on it 3 times in a row, you should get approximately the same reading. If you get 150, then 165, then 142, the scale is unreliable. The variation is what we call noise, measurement error, not real changes in your weight. So a reliable scale gives consistent readings. Step on it repeatedly, get the same number within a small margin of error. So the same principle applies to psychological measures. If you give someone a depression questionnaire today and then give them the same questionnaire tomorrow, assuming their depression hasn't actually legitimately changed, you should get similar scores. If the scores are widely different, the measure is unreliable. It's picking up noise, not real depression. Okay, there are several ways to assess reliability, depending on what kind of consistency you're concerned about. Test, retest reliability asks, does the measure give the same result at different times? Measure someone today, measure them again in 2 weeks, see if the scores are similar. This is appropriate for constructs that should be stable over time, personality traits, for example. Internal consistency asks, do the items on a scale hang together? If you have a 20-item depression questionnaire, do people who score high on some items also score high on others? If the items are all measuring the same underlying construct, they should be correlated with each other. Inter-rater reliability asks, do different observers give the same rating? So if 2 clinicians independently assess the same patient, do they reach the same diagnosis? This is important for subjective measures where there's room for interpretation. And then measuring reliability, the way we do that is the reliability coefficient. So reliability is quantified with a reliability coefficient, which ranges from 0 to 1. A reliability of 0 means pure noise, no consistency at all. A reliability of 1 means perfect consistency. So by convention, reliability above 0.7 is considered acceptable. Above 0.80 is good. Above 0.90 is excellent. So what does reliability of, say, 0.80 mean? It means that 80% of the variability in score reflects real differences between people, and 20% is measurement error or noise. Okay, that's important. Even good measures have noise. So even with a reliability of 0.90, 10% of the score variability is error. Okay. Unreliable measures cause problems. First, they add noise. If your measure is half real signal and half random noise, it's harder to detect real effects. The noise obscures what you're looking for. Second, they make your estimates less precise. So with unreliable measures, your confidence intervals are wider, your conclusions are less certain. Third, in some circumstances, unreliable measures can bias your conclusions, underestimate the relationships that do actually exist. So reliability matters. You want measures that are consistent, that give similar results under similar conditions, that minimize noise, but reliability is not enough. Okay, reliability is necessary, but it's not enough. A measure can be reliable, but be completely invalid. It can give consistent results while measuring the wrong thing entirely. Think about a bathroom scale that always reads 10 pounds too high. It's reliable, step on it repeatedly, get the same reading, but is not valid. The reading doesn't reflect your true weight. So reliability tells you your measure is consistent. It doesn't tell you your measure is accurate. For that, you need validity. Okay? Validity is about accuracy. Does the measure actually measure what it claims to measure? This is the hard one. This is the question that haunts psychological measurement and research. Because the problem is you can't directly check validity. You can't hold up true depression next to a depression questionnaire score and see if they match. You can't compare an IQ score to actual intelligence because you don't have independent access to actual intelligence. Okay? Validity is established through evidence, not direct observation. You accumulate evidence that the measure behaves the way it should if it's measuring what it claims. You never prove validity conclusively. You just build a case for it. Okay? There are different types of evidence that bear on validity. Face validity is the weakest form. It just asks, does the measure look like it measures what it claims? A depression questionnaire that asks about sadness and hopelessness has face validity for depression. It looks like it's about depression, but appearances can be deceiving, right? So a measure can look valid and not be valid. Face validity is better than nothing, but it's not strong evidence. Then we have content validity. Does the measure cover all aspects of the construct? Depression isn't just sadness. It involves sleep problems, appetite changes, loss of motivation, difficulty concentrating, and more. A depression measure with good content validity would address all of these aspects. If it only asks about sadness, it's missing important content. 3, criterion validity. Does the measure correlate with things it should correlate with? A depression measure should correlate with clinical diagnoses. People diagnosed with depression should score higher. It should correlate with functional impairment. People who score higher should have more difficulty at work and relationships. Should correlate with other depression measures. If it doesn't correlate with these things, something is wrong. Either the measure isn't valid or our understanding of depression is wrong. 4th, construct validity. Does the measure behave the way the theory predicts? If the theory says anxiety causes avoidance, an anxiety measure should correlate with avoidance. If the theory says anxiety and depression are different things, the measure should be distinguishable. They should correlate, but not too highly. And they should predict different outcomes. So construct validity is about fitting the measure into a broader theoretical framework. Does it act like the construct should act according to your theory? Validity as an ongoing argument, validity is never fully established. It's always ongoing. A measure gains validity through successful predictions. Every time it behaves as expected, confidence in the validity of this measurement grows. So a measure loses validity through failures when it doesn't predict what it should or when it predicts things it shouldn't. Validity is really an argument. It's built over time through empirical research. It's not a binary thing that you have it or you don't have it. It's a matter of degree, a matter of evidence. Okay. So let me clarify how reliability and validity relate. Reliability is necessary but not sufficient for validity. An unreliable measure cannot be valid. If depression scores are just random noise bouncing around arbitrarily, they can't be measured in depression. There's no signal, only noise. But a reliable measure can be invalid. So you can consistently measure the wrong thing. A scale that always reads 10 pounds is high in reliability but not validity. Okay, so reliability is about precision, validity is about accuracy. Precision means hitting the same spot consistently. Accuracy means hitting the target. So you can be precise without being accurate, consistently hitting the same wrong spot. You can't be accurate without being precise. If you're all over the place, you can't be consistently on target. You need both, okay? Precision and accuracy, reliability and validity. So psychology has a validity problem in its research. Many of our measures have uncertain validity. We don't always know whether we're measuring what we think we're measuring, and this matters a lot. Because if we're not measuring the constructs we care about, our findings might be about the measures, not about the actual underlying reality. So as an example, implicit association tests, hopefully you've heard of this. It's been used millions of times. The idea is that these tests reveal unconscious biases, prejudices that you have but you aren't aware of. So the way it works is you quickly categorize words and images, and the test measures your reaction times. If you're faster at associating black faces with negative words and white faces with positive words, that's supposed to indicate that you're racist. You have anti-black bias. So the IAT has been enormously influential. It's used in diversity training, it's used in hiring decisions, it's used to tell people that they're racist and they have biases that they aren't aware of. But here's the problem. The validity evidence is really weak. The IAT does not predict actual behavior very well. So people with high implicit bias scores don't consistently show more discrimination in how they actually treat people. So the IAT isn't stable. Take it multiple times, you get different scores. The relationship to actual discrimination is weak. So what is the IAT measuring? Maybe it's measuring unconscious bias, or maybe it's measuring familiarity. You're faster with familiar associations. And cultural familiarity isn't the same as bias. Or maybe it's measuring speed of processing or response strategies or any number of things. We don't know. The validity is uncertain. And yet this measure is used to make real decisions about people, is used to tell people they're biased and racist. It shapes training programs that you could lose your job over it, all based on uncertain validity. Another example, self-esteem measures. The Rosenberg self-esteem scale is the most widely used measure of self-esteem. It asks things like, I feel that I have a number of good qualities and I take a positive attitude toward myself. But what is it actually measuring? Is it measuring actual self-esteem, how you really feel about yourself? Or is it measuring self-presentation, how you want to appear to others or you think you should appear? Or is it measuring cultural scripts, what people in this culture think they're supposed to say about themselves? So different cultures respond differently to self-esteem items. Americans tend to score high, East Asians tend to score low. Is this because Americans have higher self-esteem or because it's more culturally acceptable in America to say positive things about yourself? We don't know. The validity is uncertain. Okay. Let's talk about the replication crisis again. Okay. I mentioned last time, one reason findings fail to replicate is that the original measures lacked validity. Researchers measured something, found an effect, published the finding, but they weren't really measuring the construct they claimed in some of the research. They were measuring something specific to that operationalization. So when others tried to replicate with slightly different measures, that effect disappeared. And because the effect was never about the construct, it was about that measure, okay? This is a fundamental problem. If our measures don't capture our constructs, our science doesn't accumulate. We're not building knowledge about the world. We're building knowledge about our instruments, about our measurements. So what do you do with this? You develop critical thinking about measurement. Okay, you don't treat measures as truth-telling machines. You ask, what is this measure actually capturing? How do we know it's valid? For what populations is it valid? What assumptions does this instrument make? And when you see claims based on psychological measures, again, you hold them lightly. You remember that the measure might not capture the construct. The finding might be about the instrument being used, not about reality. Okay, so this isn't nihilism. Some measures are better than others. Some have more validity evidence than others, but none of them are perfect, and you should calibrate your confidence accordingly. Okay, now I want to talk about a different kind of variable classification, one that's really crucial to understanding experimental research. Okay. When you run an experiment, you have two kinds of variables that play very different roles. The independent variable is what you manipulate. It's the cause in your causal hypothesis. It's what you do to people. The dependent variable is what you measure. It's the effect. It's what you're looking for as a result of your manipulation. Let me give you examples. You want to test whether a drug reduces anxiety. The independent variable is the drug. You give it to some people and not others. That's what you manipulate. The dependent variable is anxiety level. That's what you measure to see if the drug worked. You want to test whether a teaching method improves learning. Another example. The independent variable is the teaching method. You expose some students to the new method and others to the old method. The dependent variable is learning. Test scores, maybe. That's what you measure. You want to test whether exercise reduces depression. Okay. The independent variable is exercise. You have some people exercise and others not. The dependent variable is depression scores. That's what you measure. The independent variable is sometimes called the predictor because it predicts the dependent variable. The dependent variable is sometimes called the outcome because it's the outcome you're interested in. That would be easier to remember. Okay. I don't know why they don't just do that. So here's why this distinction is so important. Only experiments with manipulated independent variables can establish causation. Why? Because of random assignment. When you run a proper experiment, you randomly assign people to conditions. Flip a coin, draw names from a hat, use a random number generator, whatever. Make it genuinely random. So what does random assignment do? It creates groups that are equivalent on everything except the independent variable. So think about it. If you randomly assign people to get the drug or not, the two groups should be similar in age, gender, baseline, anxiety, health, history, personality, everything. Any individual characteristic should be balanced across groups by random chance. So when you find a difference in the dependent variable, when the drug group has less anxiety, you can conclude the drug caused it. What else could it be? The groups were equivalent on everything else. The only systematic difference, hopefully, was the drug. So this is the logic of causal inference. Manipulate one thing, hold everything else equal, observe the effect. So the manipulation must have caused any difference you find. So contrast this with correlational research. Okay. In correlational research, you don't manipulate anything. You just measure two variables and see if they're related. You measure how much people exercise and how depressed they are. You find a correlation. People who exercise more tend to be less depressed. Can you conclude exercise reduces depression? No, you cannot. And why not? Because you didn't manipulate exercise. You didn't randomly assign people to exercise or not. The people who exercise might be different from the people who don't in all sorts of ways. Maybe people who are less depressed have more energy to exercise. The causation actually runs backwards, so less depression causes more exercise, not the other way around. Maybe both exercise and depression are caused by a third variable. Maybe people with good social support both exercise more, like their friends invite them to the gym, and they're less depressed because they have a social support that's protective. So the exercise isn't even causing anything in that scenario. So without manipulation and random assignment, you can't sort out these possibilities. You have a correlation, but you don't know what's causing what. This is why correlational research cannot establish causation. It can show that things go together. It can't show why. We'll talk about this more when we get to correlation and regression. But for now, remember, independent variables are manipulated. That's what allows causal inference. Without manipulation, you have correlation, not causation. Okay. Now let's talk about variables that can mess things up. In any study, there are more variables than just your independent and dependent variables. There are extraneous variables, all the other things that might affect your results. Some extraneous variables are benign, okay? They add noise, make your measurements messier, but they don't really mess up your conclusions. But some extraneous variables are dangerous to your research. They're called confounding variables, and they can completely undermine your conclusions, okay? Let me give you an example of a benign extraneous variable. You're testing whether a drug improves memory. You give some people the drug, others a placebo, and then you test their memory. But here's the thing. Some people slept poorly the night before testing. Sleep affects memory. So sleep is an extraneous variable. It's not your independent variable, which is the drug, but it does affect your dependent variable, memory. So is this a problem? It adds noise. Some of the variation in memory scores will be due to sleep, not just the drug. And this makes it harder to detect the drug's effect. The effect is partially obscured by noise. But it doesn't systematically bias your conclusion about the drugs. As long as sleep isn't related to which group people are in, as long as poor sleepers aren't, more likely to get the drug or the placebo, sleep just adds random noise. It makes your life harder as a researcher, but it doesn't lead you to wrong conclusions. Okay. The dangerous ones, now let me give you an example of a confounding variable. This is different. This is much more dangerous to your research. You want to test whether a new teaching method improves test scores, okay? But you can't randomly assign students to methods for practical reasons. You let teachers volunteer to use the new method. Here's the problem. The teachers who volunteer might be different from those who don't. Maybe the volunteers are more enthusiastic, more skilled, more motivated, more interested in innovation. Now you run your study. Students with the new method score higher. What can you conclude? Is it the teaching method that caused the improvement? Or is it the better teachers, the more enthusiastic teachers? You can't tell. Teacher quality is confounded with teaching method. So the teachers using the new method are systematically different from those using the old method. Any difference you find might be due to the method or to the teacher or some combination. This is a confound. It's a variable that's systematically related to both the independent variable, which method is used, and the dependent variable, the test scores. It creates an alternative explanation for your results. And here's the worst part. You can't fix this with statistics. The confound is baked into your data. No amount of statistical sophistication can disentangle the method effect from the teacher effect. They're mixed together. Okay? So let me be clear about why confounds are so dangerous. They don't just add noise. They systematically bias your conclusions in a particular direction. So with a confound, you might conclude that the teaching method works when actually you just had better teachers. You've reached a false conclusion. You're wrong, and you don't know you're wrong. Or you might miss a real effect. Maybe the method actually does work, but the teachers using it were worse, so the effect is masked. Either way, your conclusion is wrong. And unlike random noise, which kind of averages out, confounds systematically push you towards incorrect answers. Okay. So here's why random assignment is so important. Random assignment balances confounds across the conditions. So if you randomly assign students to teaching methods, the teacher quality should be balanced. Good teachers and bad teachers should be equally likely to end up in either condition. So with balanced confounds, the only systematic difference between groups is the independent variable. And that means differences in the dependent variable must be due to the independent variable. Okay, so random assignment doesn't eliminate these extraneous variables. They still exist, but it distributes them evenly across conditions so they can't mess up, they can't confound your results. This is why random assignment is essential for causal inference. Without it, you never know whether your results are due to your independent variable or to some confound. With it, you can be confident that your independent variable is the cause. So when random assignment is impossible, here's another thing, okay? Sometimes you can't randomly assign. You can't randomly assign people to smoke or not smoke to study the effects of smoking. That would be unethical. You can't randomly assign people to experience trauma to study the effects of trauma. That would be evil. You can't randomly assign people to be male or female, or to have high IQ or low IQ, or to be from one culture or another. When you can't randomly assign, you're stuck with correlational research. You can measure things and look at relationships, but you can't draw causal conclusions with confidence. You can try to statistically control for confounds, measure them, adjust for them in your analysis, but this only works if you've measured all the relevant confounds. And you never know if you've got them all. The honest answer is when you can't randomize, you have to be humble about causation. You can say variables are associated, you can speculate about causal mechanisms, but you can't prove causation the way you can with a properly randomized experiment. So let me return to something we discussed last time because it connects to everything we've talked about today. The fundamental challenge of research is that you want to make claims about populations, but you can only study samples. The population is everyone you want to draw conclusions about: all adults, all patients with depression, all third graders, all human beings. The sample is the subset you actually study. The 200 people in your experiment, the 1,000 survey respondents. You study the sample. You make measurements on the sample. Then you try to infer what's true about the population. So this only works if your sample represents your population. Here's a problem that psychology has become increasingly aware of over the past couple of decades. It's called the weird problem. Weird stands for Western, educated, industrialized, rich, and democratic. And the problem is that most psychological research is conducted on weird samples, specifically on American college students. Why? Because they're convenient. If you're a psychology professor at an American university, you have easy access to undergrad students. They need extra credit, they need money, they show up, you can run studies. But the problem is American college students are not representative of the entire globe. They're not even representative of all Americans, right? They're young, educated, relatively affluent at a particular life stage, and they're certainly not representative of all humans. So most humans are not Western. Most are not college educated. Most don't live in industrialized, rich, democratic societies with iPhones and cars or whatever. So when researchers find an effect in American college students and claim they've discovered something about human nature, they're making a massive leap. They're generalizing from a very narrow sample to all of humanity. Sometimes this works. Sometimes the findings do generalize. I should say that. Human beings have a lot in common, and sometimes effects that appear in one population appear in the others. But sometimes it doesn't work. Sometimes effects found in weird samples don't replicate in the other populations. Okay, visual illusions that work on Americans don't work on people from other cultures. The way Americans respond to fairness games is unusual compared to the rest of the world. Patterns of memory, attention, reasoning, many of them vary across cultures in ways that weren't discovered until researchers started testing non-weird populations. And this is a problem. If our science is built on weird samples and weird samples aren't representative, then our science might not generalize to all of the other cultures. So we might be building a psychology of American college students, not a psychology of human beings. Okay. So you can only generalize to populations your sample represents. If your sample is American college students, you can confidently generalize to American college students. Generalizing beyond that requires additional argument or evidence. So if you want to generalize to all humans, you need to either sample from all humans, which is impractical, or have good theoretical reasons to believe the finding is universal. And even then, you might be wrong. This is why replication across populations matters. So finding an effect in one sample is a start. Finding it again in different samples increases confidence that it's real and general. Okay? Failing to find it in other populations suggests it might be specific to the original sample, which isn't necessarily a problem. Okay, that's good to know. So let me state this as clearly as I can. Statistics cannot fix a bad sample. If your sample is biased, If it systematically differs from your population, no statistical analysis can correct that. You will get precise answers to the wrong question. You'll draw confident conclusions about the wrong group. That's not an improvement over uncertainty. Confident wrong answers are worse than acknowledged ignorance. So sample quality matters. Who you study, how you recruit them, whether they represent the population you care about. These are not minor methodological details. They're fundamental to whether your conclusion means anything at all. Okay. So let me close by returning to the theme I introduced at the end of the last topic. The moral dimension. Measurement is not morally neutral. How we measure shapes what we see. What we measure shapes what we value. And measurements can be used to help people or to harm them. Okay? Let me give you a historical example, intelligence testing. IQ tests were developed in the early 20th century, and very quickly they were put to use classifying people. They were used to sort children into educational tracks. They were used to determine who could immigrate to the United States. They were used to identify who was feeble-minded or mentally retarded or dumb. And they were used to justify eugenics. In the early 20th century, tens of thousands of Americans were sterilized against their will. They were institutionalized and they were sterilized, so they couldn't have children because they were judged unfit to reproduce. They were not smart enough. They were unfit to pass on their genes. And part of the justification for this was IQ scores, the numbers, the measurements. The numbers felt objective. They felt scientific. They felt authoritative. They provided cover for what was being done. But the tests were deeply flawed. They were culturally biased. They conflated knowledge with ability. They penalized people who hadn't had access to education, which was especially common back then. They were normed on unrepresentative samples. They were used to measure people who weren't, represented in those norms. The numbers obscured the moral horror of what was being done. People were sterilized because of scores on a test. Lives were destroyed. Families were never started, all based on numbers that looked scientific, but were actually deeply problematic. Okay? This is an extreme example, but the principle extends to all measurement. Every measurement embodies assumptions about what matters, what should be captured, what counts as evidence. Every measurement can be misused, okay, to categorize people, to make decisions about them, to allocate governmental resources, even to justify harm. So when you develop a measure, you create a lens through which people will be seen. You should think carefully about what you're including and excluding in your research. You should consider how it might be misused. When you use measures that others developed, you should not treat them as neutral arbiters of truth. So you should ask what assumptions they embody. Who developed them? What was their reason for developing it? Are they valid for your population? How could they distort reality? Okay. So here's the bottom line. Measurement is a moral act. It's not just a technical procedure. It has consequences. It shapes how people are seen, how they're treated, what opportunities they have. Treat it as such. Okay. Be thoughtful about what you measure and how. Be aware of the assumptions you're making. Be humble about the validity of your measures, and be alert to the ways measurement can be used to harm people. This doesn't mean you shouldn't measure. Measurement is essential. Without it, we're back to intuition and lying to ourselves, and we know how that goes, lobotomies and everything. But measure carefully, measure responsibly, and never forget that numbers actually represent real people. Okay? So let me pull together what we've discussed today. Variables are anything that can vary. Whether something is a variable depends on your study design. Variables have possible values, the range of values they can take. Constructs are abstract theoretical things that we care about, intelligence, depression, self-esteem. Operationalizations are the concrete measures we use to capture constructs, IQ tests, questionnaires. The gap between construct and operationalization is fundamental. We never know what for certain that our operationalization captures our construct, and this is where validity concerns live. Okay. Levels of measurement determine what we can do with our numbers. Nominal is categories without order. Ordinal is order without equal intervals. Interval is equal intervals without true zero. And ratio is equal intervals plus true zero. Okay. Psychology has a dirty little secret that we routinely treat ordinal data as interval, and this may or may not be a problem, but you should be aware of it. Reliability is consistency. Does the measure give the same result under different conditions or same conditions? Validity is accuracy. Does it measure what it's supposed to? Reliability is necessary but not sufficient for validity. You can consistently measure the wrong thing. Psychology has a validity crisis. Many measures have uncertain validity. Findings might be about the measures, not the constructs. Independent variables are what you manipulate. Dependent variables are what you measure. Only experiments with manipulated independent variables can establish causation. Okay. We have confounding variables that mess everything up. Random assignment balances these confounds. Samples must represent populations for inference and generalization to work. And the weird problem means that psychological research may not generalize beyond, Western college students. Okay. And statistics can't fix this. It can't fix a bad sample. If it's biased, your conclusions are wrong, no matter how good your statistics are. And lastly, measurement is a moral act. It shapes how people are seen, how they're treated. Do it carefully, do it responsibly. All right, so next week we'll start talking about descriptive statistics, or next topic, central tendency. How do you summarize a distribution? What's typical? What's average? We'll talk about means, medians, modes, different ways of answering the question. If I had to pick one number to represent this distribution, what would it be? So these seem like simple concepts, but they have subtleties, and they connect to everything we've discussed today. The level of measurement affects which measure of central tendency is appropriate, and that the gap between what you measure and what you care about affects what your summary statistics means. Okay, so practice today. Notice measurement around you. Between now and next time, I want you to practice noticing measurement. When you see a claim based on research, ask, what did they actually measure? How did they operationalize the construct? Is the measure valid? When you see a number, ask, what level of measurement is this? What operations are appropriate? When you see research findings, ask, what was the sample? Does it represent the population they're claiming to generalize this to? This is how statistical thinking becomes habitual. You shouldn't just do it in this class. You need to do it all the time. You need to develop a critical eye for measurement, for evidence, for claims. And that critical eye is one of the most valuable things you can develop. It protects you from being fooled, by others, by yourself. Okay. So let me leave you with questions you should ask whenever you encounter research. 1, what construct am I actually trying to measure? 2, is my operationalization capturing that construct, and how do I know? 3, what level of measurement is this? Are my statistical operations appropriate for this level of measurement? 4, is my measure reliable? Does it give consistent results? 5, is my measure valid? Does it capture what it's supposed to? 6, is my sample representative of my population? Can I generalize? 7, what assumptions am I making about measurement? 8, how might my measurement be misused? 9, what am I actually measuring versus what am I claiming to measure? Okay, so if you ask these questions consistently, you'll be ahead of most researchers. You'll think more clearly about evidence, you'll draw better conclusions, and you'll avoid lying to yourself and fooling yourself. Okay, so that's it for today. Do the reading, think about measurement, and I'll see you next week.